that. So here's an example where we have that exact same information. We have bins defined on the x-axis. We know that there are 500 chains that are in the molecular weight range of 5,000 to 10,000. Notice the 10 to the 3 value here. The next bin has 1,600 chains that are in the molecular weight range of 10,000 to 15,000. And we can see the data evolve for the rest of the bins in this distribution of chains. So notice now that we're well past the 10 students, quote unquote, and we're dealing with now a sample that's about 10,000 molecules instead. Okay, to determine number fraction, same ideas as before. So if we were to do this bin, we're going to need to take the average, we're going to need to take the number of chains in that category, that's the 2,700, and we're going to divide it through by the sum of all chains, which is of course the 10,000 numerical we see there. Okay, so the first number fraction for the most populated set of chains here is the 0.27. That becomes our new entry right here. So there's our 0.3, 0.2, so it is right there at 0.27. That's our middle bar. Okay, so when applying that same approach to all the other entries, for example, the final one would be 200 divided by 10,000 to give us this value here. We would get that smallest bin at the highest molecular weight option, where the average is between 35 and 40,000. And for, say, the next category to the right of our tallest here, we would have 2,000 divided by 10,000, and that would give us a number fraction of the 0.2 shown here. Okay, so notice how the shape of the bins hasn't changed. These two graphs are nearly superimposable because the number fraction is reflecting the same kind of bin information, just with a different y scale. Okay, so in other words, the right graph can almost superimpose on top of the other one with just a new set of y coordinates for the tick marks on the y-axis. Okay, so with that, we can now think about the weight fraction information. So recall what we do here is we need to use a weight value in our numerator to help us with the value. So we are going to take a specific number of chains in a category. Okay, we used to do 2 students, so now we're going to do the 2,700. We're going to multiply through by the average for the limits of the bin. Okay, so I'm seeing that down here. Number of chains times the average of the bin. That's our numerator. Okay, so there that is. And we're going to divide that through by the total weight of the sample. So it's going to be by the sum of all alike results. So notice down here, this first piece is in fact the numerator of a different calculation. This is the numerator of a different weight fraction calculation. So all the numerators go into establishing the sum that is the denominator. Okay, so and again, that's an approach to determining, of course, the total mass of the sample, or if you want to remind yourself of the classroom analogy, the total mass of the class. Okay, so because we had 500 times the average of 5 and 10, that's where we're going to get the 7,500 value, etc. We get the denominator that way. So now our weight fraction value for the middle is not easily predicted by looking at the 2,700 number, but it is now a 0.29 value instead. Okay, so you can see here that ultimately by doing the alike calculation, where we take turns swapping the numerator for the different pieces down below, that we can build up the new graph, and that the shape of this new graph is shifted to the right. We're putting the sort of average of this bar chart more to the right than what we saw in the number fraction information and graph that was of the same shape as this with a different y-axis. Okay, so hopefully you can see visually now how we get a weight fraction average mass for the chains that is now at higher x coordinate than the number fraction approach. Okay, so here's some of that data, and we'll just kind of carry it through to determine, for an example, determine the number average molecular weight using that information. Okay, so hopefully it's easy for you to see how we would get number fraction information now. Again, going back to the classroom, that's like 2 divided by the 10 students, number of chains divided by the total chains, and we can get all these values. So we saw a moment ago that 2,700 chains divided by the 10,000 gave us that value. So hopefully you're comfortable getting all the xi values here. Okay, so here's that same information again against the beginning and end of each bin. And now, taking the average of the limits of the bin, we have the mean average of that bin. This allows us to now think about multiplying these two together to give us the mi xi values. And we'll populate that down the row here as part of the next step to determine the number average molecular weight for this polymer distribution. So let's just clean that up because I believe I have that nice and formalized for us here. And so there that is, xi times mi, and we have the outcome of simply multiplying this column times that column to give this. Okay. And then, to simply determine the number average molecular weight, we have to sum up all of those values. So sum up xi and mi values. Okay, so we see that reflected right here, of course. So all we're going to do is then sum all of these up, and we're going to get our mn average. Okay, so in doing that, we end up with 21,150 grams per mole for the value there. Okay, so here's our mn value. Good. Okay, so like we did the calculation for the 0.29 earlier, we could now think about doing all of the bin options there for the weight fraction. And the weight fraction again was taking the number of chains times the average mass of the bin divided through by the total mass of the sample. Okay, so we can see here in calculating the version here that we would be looking at 22,500 times the total weight fraction of 0.29, and we would divide through by the total mass of sample. Okay. Good. So that information is kind of reflected here now. Here's that average between the limits of our bins, 22,500. We saw that we were going to use the 0.29, and so those two multiplied together are going to give us a 6525. Okay. So in other words, again, taking the mean for the bin's limits, okay, 20,000 on averaged with 25 is going to give that number, of course. And then we multiply through by the weight fraction information. We should be getting these entries here. Similar to what we saw before, if we sum all of this up, we're recalling that the mass fraction by weight is going to be the sum of all wi mi values. We simply have to sum this up, and we'll get the value for MW average. Okay, so notice here the value is 23,200. This is a larger value than we had in the 21,150 for the MN value. Okay. So now kind of reporting all this on top of the data that we were provided, we see here that in returning to our ideas here, that the graph kind of evolves in shape as we consider a number fraction xi approach versus a weight fraction approach. And so we shift the shape more to the right. The kind of curve over top of that helps us see that the midpoint of the curve here is more closer to 20,000 molecular weight, and that corresponds to a number average of 21,150. And we do the same thing by applying a curve to the data that is now weighted by a weight fraction, that our value is higher at about 23,200 instead. Okay, so there's an example building off ideas that we established for students in a classroom and now applying it to chains that are differing from one another by their mass. Okay, so that brings us to the end of the video. Hopefully you're able to follow that. Please do email me if you have any questions about that, and I encourage you to practice some homework problems while this is fresh in your mind. Thank you very much.